Swayam Prabha. Digital India. Educated India.
A warm welcome to the 17th lecture on the subject of digital signal processing and its applications. We use this lecture to build a few more ideas in the context of system theoretic concepts in the Z domain. So, in the previous lecture and in the lecture before that, we had looked at the rational Z transform in detail. In the previous lecture, we also saw an example of an irrational Z transform. And we also explained, what we meant by a rational Z transform in detail, what the consequences were in terms of invertibility and so on. Now, what we need to do is to look at systems which have rational impulse responses, in other words, rational systems, and we wish to characterize those systems from the point of view of other properties that an LSI system may or may not have. So, in fact, let us quickly recapitulate. We have so far talked about rational systems. So, rational systems are of course LSI. They are LSI systems whose impulse response has a rational Z transform. Incidentally, we also talked about the importance of rationality from the point of view of being able to convert a system into a realization. We saw last time that a rational system can be realized. In fact, a rational system can be realized with an LCCDE, a linear constant coefficient difference equation. And a linear constant coefficient difference equation can be translated into a hardware or a software structure. We saw that too, right? In fact, we saw a specific form of realization last time. There are other ways in which the same rational system can be realized, and in fact, we shall be spending quite some time on the subject of realization of rational systems later. However, at this time we have assured ourselves, we have convinced ourselves by example that it is possible to realize any rational system by converting it into a corresponding linear constant coefficient difference equation and then realizing that linear constant coefficient difference equation. Now, what we did not carefully note last time was that the system that we had realized was also causal. Stable is not an issue. You can realize both stable and unstable systems, but realizability also does depend on whether the system is causal or not. I mean, there are two ways of looking at it. One is that if you are dealing with the system in real time, then unless the system is causal, it cannot be realized, because you cannot have future samples available to you when you are processing the current sample. That is one way of looking at it. The other way of looking at it is, even if you did, the structure of the system must be such that there is a unique way in which you can proceed with the computations of the samples. If that is not true, there is a problem. Now, instead of trying to explain this in general, we would look at the requirements on a rational system for it to be causal and stable, and thus convince ourselves of the context in which we want to remain in the future now. Instead of trying to look at all possible things that we may not be able to realize, it is much more meaningful to look at what we want. Namely, we want a causal system, we want normally a stable system if you want it to have a frequency response. And in that case, we need to characterize the rational system by looking at its poles and zeros and anything else that characterizes it to see if the system is causal and stable. Now, let me put down the problem that we are trying to address. clearly. Issues. A rational system is of course linear shift invariant. But is it causal? Is it stable? May or may not be. In fact, it is not at all difficult to see that there are examples of all possibilities. Causality and stability are independent properties. You may have four kinds of rational systems: those that are not causal but stable, those that are causal but not stable, those that are neither causal nor stable, and those that are both causal and stable. In fact, I go back to the examples of the rational transform that we have dealt with to date. So, let us look at the rational system with system function one by 1 minus half z inverse 1 minus 2 z inverse. Now, please note, the moment I write this, you should immediately ask me what is the region of convergence. I told you we often forget that a rational system must be characterized by both an expression and a region of convergence. So, here I have three possible regions of convergence. Let us look at each of them in turn. Let us look at the region of convergence mod z between half and 2, in which case the impulse response, I leave it to you to complete the working, but I will straight away write down the answer. The impulse response would become some constant. I mean, in fact, let us do one thing. Let us complete the working by decomposing this into partial fractions first. So, you have a term in half z in 1 minus half z inverse, and you have a term in 1 minus 2 z inverse. So, when I want the term in 1 minus half z inverse, I multiply by 1 minus half z inverse and put z equal to half. So, I have 1 minus 2 by half, or 1 minus 4, that is 3 minus 3. And then I multiply by 1 minus 2 z inverse and put z equal to 2. So, I have 1 minus 1/4 in the denominator, that is 3/4, so 4 by 3. Am I right? In fact, just for convincing ourselves, let us verify that this is indeed the decomposition. You do not need to do this every time, but I am just doing it a couple of times to convince you that we are doing the right thing. So, minus 1 by 3 divided by 1 minus half z inverse plus 4 by 3 1 minus 2 z inverse can be put together. 1 minus half z inverse 1 minus 2 z inverse minus 1 by 3 1 minus 2 z inverse plus 4 by 3 1 minus half z inverse. And we can see that the constant term is 4 by 3 minus 1 by 3, that is 1. The coefficient of z inverse is minus 2 by 3 plus 2 by 3, that is 0. And therefore, we have this equal to 1 by 1 minus half z inverse 1 minus 2 z inverse. Anyway, now we see that the system function can be rewritten as minus 1 by 3 1 minus half z inverse plus 4 by 3 1 minus 2 z inverse. And we need to invert this for each case of the region of convergence. So, as I said, let us take the first case as we have considered, namely mod z between half and 2. Now, when mod z is between half and 2, for this mod z is greater than half. So, you have a right sided sequence coming out of this, and for this mod z is less than 2. So, you have a left sided sequence coming out of this. So, all in all you get the impulse response h n to be minus 1 by 3 half raised to the n u n plus 4 by 3 into minus 2 raised to the power of n u minus n minus 1. In fact, let us sketch this impulse response sequence to get an understanding. You see, half raised to the power of n starts from 0. So, you have 1 half, 1 half squared and so on, isn't it? This is half raised to the n. Similarly, 2 raised to the power n u minus n minus 1 begins at minus 1, and at minus 1 it takes the value minus 2 raised to the minus 1. So, minus half. At minus 2 it takes the value minus half squared and so on and so forth. So, this is 2 raised to the power of n minus 2 raised to the power of n u minus n minus 1. This is right sided, this is left sided. And you can put them together. You take minus 1/3 times this sequence plus 4 by 3 times this sequence. Of course, luckily they do not overlap. So, anyway it means you just multiply the corresponding samples either by minus 1 by 3 if they are between 0 and infinity, or by 4 by 3 if they are between minus 1 and minus infinity. Easy. So, we know what the impulse response is. And in fact, here we can find the absolute sum of the impulse response with great ease. We can easily see that the absolute sum is very easy to calculate. It is 1 by 3 summation n going from 0 to infinity half raised to the n plus 4 by 3 summation n going from 1 to infinity again half raised to the n, and that is 1 by 3 1 by 1 minus half plus 4 by 3 into half into 1 minus half. And of course, you can simplify this, but anyway it is absolutely summable. So, clearly this system is stable. Now, we take the second region of convergence, mod z greater than 2. And there of course, you have the impulse response to be very simple, 2 raised to the power of n u n plus half raised to the power of n u n. Incidentally, the system that we have just seen is stable, but not causal. That is easy to see, because the impulse response is not 0 for all n less than 0. So, system is not causal. But here we have a causal system here, but clearly unstable. That is because summation n going from 0 to infinity 2 raised to the power of n diverges. that arises from here, that term diverges. So, the system is unstable. Now, we take the third region of convergence. Mod z less than half, whereupon we have minus half raised to the power of n u minus n minus 1 minus 2 raised to the power of n u minus n minus 1. Of course, by the way, a little correction here, I should put the factors along with it. Yes, 4 by 3 and yes. So, so it's a linear combination. So, say factor here and factor here. I am just in general writing, so 4 by 3 and minus 1 by 3. The factors should come. So, that correction should be there. Here again the factors should come. 4 by 3 and minus 1 by 3. That is okay. That does not seriously affect the result. But clearly, this is totally a left sided sequence, this is non causal. And here it is not this, but this term that creates the problem. Half raised to the power of n u minus n minus 1 is the troublesome term here. It in fact becomes a growing exponential. So, this is the troublesome term. The system is unstable because of this term. It is not summable, it is not absolutely summable. So, we have an example of all three kinds: non-causal and unstable, causal but not stable, and not causal but stable. Okay. So, both negatives, one negative and one positive, Now, both positives, we want to see an example of both positive, that is of course very easy. So, if you have the system LSI system with impulse response h half raised to the power of n u n, the system function is 1 by 1 minus half z inverse mod z greater than half, and this is both causal and stable. So, now we have an example of all four. And in fact, we will take this example or this pair of examples to draw some conclusions. You see, if you notice, among the three regions of convergence for the first example, it was only one region of convergence that gave you a stable system. The region of convergence which included the unit circle, where the frequency response was defined. In the other two cases, there would be no frequency response defined. That is because the unit circle is not included in the region of convergence. So, it looks like the unit circle has something to do with stability. In fact, we will soon see that that is really what matters in a rational system, whether the unit circle is a part of the region of convergence or not. Secondly, we noticed that causality really related to being right sided, that is to be expected. If you want the system to be causal, the impulse response must be one sided, and if at all one sided, right sided. And otherwise, of course, it must be a finite length and all the samples must be at 0 or afterwards. So, right sidedness is required. Now, when you have right sidedness, then the region of convergence is outwards, beyond a certain circle. If the sequence is left sided, the region of convergence is inwards, inside to the interior of a certain circle. So, being interior and being exterior, this matters in causality. And how far exterior can you be? All the way up to infinity. So, whether or not z tending to infinity is included has something to do with causality. Now, we will formalize this. You see, first let us prove the simpler of the two results. Let us prove that an LSI system is causal and rational. Well, actually it does not have to be rational. I will not write and, I will say it is causal if its system function note we are assuming it exists. That means the impulse response has a Z transform. If its system function converges as Z tends to infinity, or you can say as mod Z tends to infinity. That is very easy to see. In fact, if a system, if an LSI system is causal and if it has a system function, then the system function must be proof. The system function Hz must be summation n going from 0 to infinity Hn z raised to the power minus n. Note, because the system is causal. Because the system is causal, you are sure that there are no samples before 0. Now, you see, as mod z tends to infinity, we can consider mod Hz. Mod Hz is mod summation n going from 0 to infinity mod Hn z raised to the power minus n. Now, this converges for some z's. So, you know the system function exists. Now, as mod z tends to infinity, z raised to the power of n tends to 0 for all n greater than or equal to 1. That is easy to see. And therefore, all the terms vanish except for n equal to 0. As mod z tends to infinity, therefore, mod Hz simply becomes mod H0. So, it definitely converges. Now, this is the if part. What about the only if part? So, can a system, you see, so what we have said, what we have proved here is that if mod z if a system is causal, then its system function must converge as mod z tends to infinity. So, here we are. In fact, what we have proved here is only if in the theorem, but what we do wish to prove is if and only if. What we have just now shown is that if a system is causal, which assures us that Hn is 0 for n less than 0, then the Z transform, we assume the Z transform exists, must converge for Z tending to infinity. We have shown that. Now, we need to prove the converse. The converse is, if the Z transform converges as Z tends to infinity, then the system has to be causal. Okay. Is that clear? Is it clear what we are trying to do? It must be proved both ways. Now, I give you the scheme of the proof, I leave a little bit of the proof to you. I give you the scheme of the proof and I leave you to complete the details. You must also prove the converse. If the Z transform, if the system function converges as mod Z tends to infinity, the system is causal. Now, the scheme of the proof is essentially that we can prove it by contradiction. So, we assume that H Z converges as mod Z tends to infinity, but we dare to assume that the system is not causal, which means that it has some non-zero samples on the negative side. That means there is at least one sample, one n less than 0, say n equal to minus n 0. Of course, n 0 is greater than 0 here, for which the impulse response is not 0. The key to the proof is that H Z would have a term h minus n 0 z raised to the power mod n 0. Arising from that impulse response sample. Okay? And of course, remember, not just one, there can be several such samples, right? There can be, I mean, if a system is non-causal, there can be several, there can be infinite such samples. The key to the proof is that if the system is causal, then can there be negative non-zero samples given that such a term comes up. Such a term has a z to the power mod n 0, so a positive power of z. And what happens as z tends to infinity? What happens as mod z tends to infinity here? For any one such term, it is obvious that that term will blow up without bound. Now, the key or the crux of the proof is, and this I am leaving to you to reflect upon, is if you have multiple such samples, can it possibly happen that this sum of positive powers or linear combination of positive powers of z can go to 0 all over the contour mod z going to infinity? You see, mod z going to infinity is a contour, not a point. So, it is a concept, it is a contour, it is a growing boundary, right. Now, on this boundary, is it possible that all these positive powers of z can be linearly combined to be 0 all over that infinite contour? Can it happen? Well, intuitively it is clear that it cannot, and I leave it to you to reflect more and see if it can at all, right. In any case, what I do leave it to you to reflect upon and conclude is that if the system is rational and causal, then this can certainly not happen, right. So, I leave it to you to complete the details of the proof based on this concept. Okay. So, exercise, complete the proof of the theorem. A rational LSI system is causal if and only if mod z tending to infinity is included in the region of convergence. This is the system function of that LSI system, of course. Now, we ask the question in the context of stability. Now, for stability, if you have rational systems, we have seen immediately what kind of impulse response to expect. In fact, in some sense, rational systems have now become very predictable to us. There are only two types of terms, or in fact, I would say only three types of terms that can come out of rational systems. Is that right? Impulse response terms. You see, that is because if you have the rational system function h z, it can always be decomposed as a finite series in z or z inverse plus a sum of poly x terms, poly x unilocated pole terms. Poly x means essentially terms which correspond to a polynomial in n multiplied by an exponential term. And how do they look in the z domain? They essentially look like in the denominator you have one pole repeated more than once or more than once, and the numerator you have a degree one less than the degree of the denominator. That's how the z transform of a poly x term looks. So, in the partial fraction expansion you have a finite series plus a sum of such terms, unilocated poles, and the poles may occur with multiplicity of more than 1, and in the numerator you have a degree up to 1 less than the degree of the denominator, and in the time domain this corresponds to a poly x term. Now, you see, I make some remarks. The first remark I make is the finite series part contributes a finite length impulse response term. This cannot affect stability. This cannot affect stability either way. So, if the system is, if the other terms make the system stable, this cannot make it unstable. That is because at most this will contribute a sum which is equal, if you take the absolute sum of all these samples, that is finite, and they cannot perturb the absolute sum of the impulse response to more than what their own absolute sum is. So, it is very clear that this cannot affect the stability of the system either way. The system is unstable, it will continue to be unstable even if you have these terms, this finite series here. So, either way it has no effect. So, we can even neglect that finite series part. Now, we look at the poly x terms. Now, what we show is that if any one of the poly x terms diverges, then the sum has to diverge, right. So, the next remark that I make is any one divergent poly x term causes the absolute sum to diverge. to understand this is a slightly deeper issue. Why does this happen? What is a poly-X term? A poly-X term is a term of the form alpha raised to the power of n times a polynomial in n. Either right sided or left sided. Now, you see a poly-X term diverges. Diverges means its sum tends to infinity. That happens if and only if mod alpha, you see, if this exponential grows or the exponential does not decay. That is a better way of saying it. So, if the exponential remains steady, there is a problem. That is, mod alpha equal to 1 also is a problem, right. But if the exponential grows, so if it is left sided, the exponential will grow if mod alpha is less than 1, and if it is right sided, the exponential will grow if mod alpha is greater than 1, right. So, divergence means growing exponential. The polynomial does not matter. You see, the polynomial can never dominate the exponential either way. If the exponential decays, even if the polynomial is growing, which it would anyway, either way, it does not affect the decay. An exponential always overpowers a polynomial, either way. So, the polynomial again does not affect divergence or convergence. It is the exponential which does. So, you see, left sided means if it is a growing exponential and left sided, that means mod alpha is less than 1. If it is a growing exponential and right sided, it means mod alpha is greater than 1. Is that clear? For example, if alpha is half, then the left sided exponential here will be divergent. If alpha is 2, the right sided exponential will be divergent. Now, why is it that we are saying that any one divergent term, one bad apple spoils the rest? Why is it that one divergent term kills all? That is because poly-X terms are linearly independent. Poly-X terms are linearly independent for distinct alpha. That means you can never have two poly-X terms which combine to 0 all over the n axis if they have distinct alpha. I leave it to you to prove this. Exercise, prove this. What I mean by that is, you cannot have two poly-X terms with different alphas which add up to 0 all over the integer n. If the alphas are distinct, their sum cannot be 0 all over n. So, one cannot cancel the other, that is what we are saying. If one of them is a rotten apple, it is bound to cause the others to rot as well. It cannot be cancelled by anyone else. That is the problem. So, now where are we? You see, if there is one rotten apple, that means if there is one poly-X term which diverges, our stability is gone. When will that poly-X term diverge? When either mod alpha is equal to 1. If mod alpha is equal to 1, that means the pole lies on the unit circle. So, pole lying on the unit circle gone. system unstable. Now, if the pole, if mod alpha is greater than 1, then you want a left sided term. What do you mean by left sided term? The region of convergence must be inside mod z equal to alpha, mod z equal to mod alpha. So, let us write it down. For stability, we want for every poly x term, mod alpha not equal to 1, mod alpha equal to 1 immediately disqualified. If mod alpha greater than 1, ROC mod z is less than mod alpha, because we want it to be left sided. Is that correct? If mod z, if mod alpha is less than 1, then we want the ROC to be mod z greater than mod alpha, because it is right sided. So, what are we saying in effect? There cannot be a pole on the unit circle. If there are any poles with magnitude greater than 1, the region of convergence must be to the interior of such poles. If there are any poles with magnitude less than 1, the region of convergence must be to the exterior of such poles. So, where can the region of convergence be? It must be between the biggest pole or the pole of largest magnitude with magnitude less than 1 and inside the pole of smallest magnitude with magnitude greater than 1. And what does that mean? That means the unit circle must be in the region of convergence. Unit circle in the region of convergence is sufficient and necessary if the system is rational and stable. Okay, so we write the theorem and I leave it to you to put down a formal proof based on what we have just discussed, and with that then we conclude this class. The theorem is a rational LSI system is stable if and only if I double f mod z equal to 1 is in the region of convergence. And of course, now we know what happens when you want the system to be both causal and stable. If you want the system to be both causal and stable, the unit circle must be in the region of convergence, mod z tending to infinity must be in the region of convergence. And the region of convergence is a simply connected region, so you can't have pieces. That means all the region from the unit circle up to mod z tending to infinity must be in the region of convergence. Okay, there cannot be any poles outside the unit circle, all the poles must be inside the unit circle. So, we conclude with that remark that if a system is both causal and stable and rational of course, then all its poles must be inside the unit circle. We shall proceed to see more from this point onwards in the next lecture.